So 9-2 is sort of a throwback to geometry again. Thankfully, they didn't put like 6 or 7 lessons into one chapter like they did in 9-1. But this one's talking about angles and stuff. So there's a couple of vocabulary words that you sort of need to know in order to really understand what they're trying to say in certain locations. Like they'll throw the terminology at you and they'll expect you to know exactly what they're talking about. And if you don't, it gets a little confusing. You know, you're asking yourself, wait, is this the initial or is this the terminal? What do they mean by standard position? Things like that. So first things first, standard position is when the vertex of an angle is at the origin, right here, at the origin of a coordinate plane. And the initial side, which we'll define in a second, lies on the positive x-axis. Okay, so that is the first vocabulary word for you, standard position. The next one is initial side. The initial side, you can sort of think about it, it is a fixed ray. It's a fixed ray that never moves and represents sort of the starting position of an angle. So you are starting off on sort of this particular location. All right, so that is your initial side. Now your terminal side, think about like a terminal that you are going to go somewhere. It's sort of like your end position of the airport before you leave the airport. So terminal is a ray that rotates around a certain degree. So this is our terminal side right here. It is going to rotate around. It could stop here, it could stop there, it could stop over here. It doesn't really matter. Notice how the terminal side is sort of going to follow this circle because it's just rotating around. So you can think about this as your, like, not starting point, but your ending point, all right? And so all we're going to do in example 1 is sort of draw our initial and our terminal side. And before we do that, I do want to just take a couple of seconds and draw out sort of the I wouldn't say the most common, but just divide up our circle that we sort of have right here and have sort of an understanding of where certain degrees are going to be. So for example, this is 0 degrees, all right? And we know that if we go around in a circle, that a circle is 360 degrees. So if I go all the way around here, I'm going to end up at 360 degrees. If I go halfway, I can just take my calculator and I can figure out that this is going to be 180 degrees. And I know that because this is a right angle, that technically this is 90 degrees. So really from here to here is 90, from here to here is 90, because 90 plus 90 is 180. If I wanted to keep going, I could get another 90, which is going to give me 270. And then if I go again, I have 360, okay? Well, these are some pretty understandable degrees, but what about in between it? If I were to go in between 0 and 90 degrees, this would be 45 degrees. And if I were to go in between 90 and 180, I can say, well, 90 plus 45 is going to give me 135. Again, I can take sort of the average of 180, or the halfway point, the midpoint, if you want to think about it, the midpoint of 180 and 270, that's going to give me 225 degrees. And then the midpoint between 270 and 360 would be 315 degrees. So I'm just sort of having this idea of where my degrees are, just so that when I start drawing it for example 1, it's easy to know, 30 degrees is going to be between 0 and 45, so I could say this is 30 degrees. If I was given something like 65 degrees, I know that 65 degrees would be beyond that, so 65 degrees. So it's just sort of helping me break up my circle so that when they give me degrees in a second, I know, is it going to be closer to 0? Is it going to be closer to 90? Is it going to be closer to 315? Things like that. It's just helping me get an idea of where things are. Okay, so here's example 1. It says draw an angle with the given measure in the standard position. All right, so I know that if I'm going to draw this, it has to be on the coordinate plane because that's where standard position is going to be for my angles. Right, so I know that the vertex is going to be right here at the origin, and I know that it is its initial ray, or its initial side, is going to be on that x-axis. All right, 240 degrees. So I went ahead and I redrew my, my sort of separated angles over here so that I can use that. And I'm going to go ahead and just figure out really quickly, okay, well, 240 is between the 225 and the 270 somewhere, okay? So I'm going to separate this so that I know, where each piece is, and I can easily see that my terminal side is going to be, again, between the 225 and the 270. So I'll label this 240 degrees, and I'm going to draw a circle just to show which way I am moving, okay? When you have a positive degree, you're going to move sort of counterclockwise. Counterclockwise. All right? So then the next one is 500 degrees. Now 500 degrees is more than 360 degrees. So I'm going to first off draw my coordinate plane. I'm going to put my little separation mark so I know where it's at. And I don't really know where 500 is, so I'm going to take away 360 just so that it's a little bit smaller. I know 360 is one complete rotation around my circle. All right, but I don't know how much farther it goes, so that's why I'm subtracting 500 from 360. 360 is one rotation, one complete rotation around my circle. So 500 minus 360 going to give me 140. So 140 is just beyond that 135 mark. All right, so I'm going to say my terminal side is right around here, 135 degrees. So I'm going to take my circle that shows that I'm moving, and I'm going to extend it to 135 and stop right there. So that is my my drawing for that. So whenever you go over 360, just subtract and see how much farther you have to go. Sometimes you only have to go one extra rotation. Sometimes you have to go two extra rotations. So what if we go backwards though? So like in this next one, we have negative 120. So again, I'm going to take my coordinate plane. It's a terrible coordinate plane. All right, I'm going to put my little separation marks just to help me out a little bit. And you could, if you wanted, just start going backwards and like counting, but that's really confusing. So what I'm going to do is I'm going to think about it as, well, what if I were going the opposite way? So I'm going to subtract 120 from 360. And when I do that, I'm going to get 240 degrees. Okay, so that's the same position as I had in part A. So I know that my 240 is going to be, or no, I'm sorry, I can't label it 240. I'm going to label it negative 120 degrees. All right, here's my terminal side, or excuse me, my initial side, and this is my terminal side. And because it is negative, all right, so a negative degree, you move clockwise. Clockwise. All right, so this is moving this way, all right? Again, I just subtracted it, so right here, I just subtracted it from 360 just to ask myself, if I were going a positive degrees, all right, then it would be going this way, counterclockwise. It just gave me my same position. It's just easier to work with when it's positive because I already have my picture over here. Than it is to work when it is negative, okay? So I'm gonna do letter A right here just one more time. I'll let you guys do B and C, and you can compare your answers on my teacher answer key, which is online. So again, draw your coordinate plane, put your little separation marks, negative 50, all right? It's hard to work with when it's negative, so I'm just gonna subtract it from 360, and I should get 310. So 310 is just shy of this 315 mark. So I know that my initial side always starts here, and 310 is gonna be right around here, and I am moving I'm moving clockwise because it is a negative degree, all right? So I'm moving this way, and that is all we're doing for this. So the reason why I was able to find my negative degrees from subtracting it from 360 is because of an idea called our coterminal. Our coterminal is when you have the same initial side and the same terminal side, so nothing changes right here and here, nothing changes, but they have different degree amounts. So you can think about this as like, let's say we wanted to find 30 degrees right here, which is what we have, all right? 30 degrees, write that right here. I took this before and I subtracted it, when it was negative, I subtracted it from 360 to find my coterminal, right? But you could, even with a positive degree, find the coterminal with 1 rotation or 2 rotations, so I can go 1 complete circle or 1 rotation around my circle and end up at the same spot. And so really you can sort of find this by the formula where your alternative theta is going to equal your initial theta by either adding or subtracting 360 degrees n number of times. And later on we'll get into radians, so the radians will be your initial radian plus or minus 2 pi n. And we'll get into that later. We're really going to be focusing on this one right here. So let's go ahead and just add 360 and see a coterminal of 30 degrees. If I add 360 to 30, I'm going to end up with 390 degrees, okay? So 30 degrees is just like this. All right, let's change the color so you can see it a little bit better. Here's my initial side, and there is my terminal side, okay? So it's very, very small. But if I do one rotation, well then I'm still ending up at this spot, but I'm going around 1 complete time, and then I am stopping, okay? So if I were to add 360 again, well now I'm at 750 degrees. This is 2 rotations. So again, I'm stopping at the same point, but I'm going around 1, 2 times, and then I'm stopping at the same location. And you can do this by adding 360 or subtracting 360, okay? So let's say I wanted to subtract 360 this time. So this is going to be 360 minus 30, or actually think about it as 30 minus 360. We're going to end up with a negative 330 degrees. This is again going to be stopping at the same location, but instead of going counterclockwise, I'm now going to go clockwise. All right, so it doesn't matter if you're going clockwise or counterclockwise with your positive or negative degree. As long as you are ending at the same location, you're good, okay? So let's do a couple of examples. Sometimes this looks a little crazy, but let's do a couple of examples. All right, so the instructions for example 2 say find 1 positive and 1 negative angles. Positive and 1 negative angles that are coterminals to the given angles. And the bells are still working. All right, so we are going to, I'm actually going to just add, and this is the most common one that we're going to do. I'm just going to make this 1 rotation. And so really we're just going to be adding and subtracting 360 degrees. We won't have to worry about this. So whenever you see this, this is typically what you're going to be doing. But let's do the formula. The formula for this is going to be our theta, our original theta, whatever they gave us, plus or minus 360. And again, I already said it's 1 rotation, which is technically a times 1, and anything times 1 is itself. So that's why we're just adding or subtracting 360. So I'm just going to set this up, negative 45 plus 360, and then negative 45 minus 360. So I'm going 1 rotation clockwise and then 1 rotation counterclockwise. So if you take negative 45 and you add 360, you should end up with 315 degrees. And then if you go clockwise, then you're going to end up with a negative 405 degrees. So that's all we're doing here, adding and subtracting 360. All right. So the next one, same thing again, 395. And it doesn't matter how big the initial degree is, has no bearing on our process. We're just adding or subtracting 360 each time. This is going to give me, if I add 755 degrees, and then our, if we subtract it, we'll end up with 35 degrees. All right, so these are our answers. I'm not going to do letter C so that you guys can get used to doing it by yourself, and just make sure you compare your answers to my answer key online. All right, for this next one, I'm actually going to do 2 rotations. Okay, so when we use the formula, all right, I'm going to plug in to the formula this time. We have our 230, that's our initial, plus 360 times 2. Remember, n is the number of rotations. N is our number of rotations. And so since I'm specifying our 2 rotations, I am plugging in a 2. So then if I were doing the same thing again, I need to subtract 360. All right, and so you can just use a calculator, type in the whole thing as is, and it should give you an answer of 950 degrees and negative 490 degrees. Negative 490 degrees. All right, same thing again with our next one, negative 135, and I'm just going to shorten this up a little bit, plus or minus 360 times 2. Remember, this is our number of rotations. If it doesn't specify, all right, if it doesn't specify the number of rotations, please do 1 rotation. All right, so if we are doing 2 rotations for this letter B, then counterclockwise, we will end up at 585 degrees, and clockwise, we will end up at negative 855 degrees. All right, so this is how you do example 2. So the other thing from geometry that we learned was that we can convert our degrees into radians. And so the question is, what are radians? Well, as I said, angles can be measured as radians, but a radian is a ratio of the length of an arc, okay? Our length of our arc is going to be right here. Just bring this over. This is our length of the arc, and the given, and this is what you need to fill into your blank, and our given radius. So really what they're saying here is that what they're doing is whatever your radius is, if you were to take this distance, r, and put it on the edge of your circle, r, then this would equal 1 radian. All right, so think about it as degrees is a measure of the corner, right? Our degrees is a measure of a corner, but our radians is just a distance of how far it goes. So think if we could like put it on a ruler, basically. So this is going to be really helpful when we have certain problems that are asking us to find area or surface area or perimeter, distance, things like that. Because again, a degree for the angle is just the measurement of a corner, but a radian is sort of like a ruler. It tells us how far things are. And so there's this nice little conversion thing right here, okay, which is super duper helpful. I recommend that you definitely do that or pay attention to it. This is when we are going from radians to degrees, and then if we wanted to go the opposite way, where degrees to radians, then we would multiply it by our new piece of information right here. All right, so knowing that is extremely helpful, and we can use this to do example 3. So example 3 says convert the degree to radians, or the radian to degrees. All right, and I tried to keep it so that you had all your degrees on the left-hand side, so you could get used to that, and then all the radians on the right-hand side. But the process is still the same. So I'm going to do example 3.1, A and B, as well as 3.2, A and B. I'll let you do C by yourself. Actually, I will do C on 3-2 just so you guys can get used to that. But after you are done sort of practicing it on your own, please make sure you compare your answers to my answer key. All right, so we have the 120, and this is degrees to radians, so I'm going to be using this bottom one right here. 120 times pi over 180. After you multiply this, think about it as multiplying across. That's over 1. So it'd be 120 pi over 180. If you type this into the calculator, it's going to give you 0. It's going to be a really crazy number. The easiest way to do this is to ignore the pi for a second. And if you ignore the pi, it's going to say 0.666666, and it's 6 repeating. Convert that into a fraction, and you should get 2/3. and then just put the pi back when you're done. So our answer will be 2/3 pi, or 2 pi over 3, however you want to say that. Same thing again with the next one, 135 times pi over 180. All right, so this would be 135 pi over 180. If you ignore the pi and plug this into the calculator, it's going to give you 0.75. Convert that into a fraction, and you should get 3/4, and then put the pi back in the numerator. So our answer will be 3/4 pi, or 3 pi over 4. Again, it doesn't matter to me how you word that. All right, so that is pretty straightforward for converting our degrees into radians. All right, so now let's do the opposite. Let's convert it from radians to degrees. Well, all we're going to do is we're going to take this and we're going to flip it. And this is so that when we flip it, okay, take this and multiply it by 180 over pi. The whole purpose of this is so that our pi crosses out. So this crosses out, and we should end up with negative 180 over 12. Okay, negative 180 over 12 should give me a negative 15 degrees. Negative 15 degrees. So we'll do the last one more time, or letter B, I should say. 180 over pi, because that's what I want to cross out. I want to cross out the pi, so it goes in the denominator. Cross those out. 5 times pi gives me 900 over 4. 900 divided by 4 is equal to 225 degrees. 225 degrees. All right, so let's look at letter C. Letter C says negative 6.28. It doesn't tell me if it's in degrees or radians, but because there is no degree symbol, it's an understood radian. So I'm going to multiply it by 180 over pi. And so really, this one you just got to plug into your calculator. Negative 6.28 times 180 divided by pi. And please make sure you're using pi, not the rounded 3.14. There is a button on your, or there should be a button on your calculator with pi, so you need to use that. Once you do that, it should be a negative 359.8 something. You can round that to the nearest degree. So if you get a decimal, just round to the nearest degree. Okay, and so that would be a negative 360 degrees. And if you're ever like concerned that maybe it's not quite right, you can go the opposite way, because it's a relationship. So if it's true for one way, it's got to be true for the other way. So if I wanted to, I can take negative 360 and I can multiply. I'm just going the same way. I'm trying to see, is my answer going to equal negative 6.28? So 360 degrees times, I'm trying to cancel out the degrees, so it's going to be pi over 180 degrees. All right, this is going to give me a negative 2 pi. If I plug in negative 2 pi into my calculator, I get negative 6.28, etc. So this is actually true. This is actually a negative 360 degrees. Again, that's just showing you that the work that we did right here, the work that we did, if we go the opposite way, we end up with the same answer. So I'm just double checking my work because I wasn't quite sure. All right, so if you're ever concerned, just do the same process again. So I'm not quite sure where our video sort of stopped. My recording didn't quite work, but here is our quote-unquote unit circle, and this is just the most common degrees that we end up with. So at the beginning of our circle, we haven't really moved any, so we would say that this is 0 degrees. 0 degrees. If we were to go 90 degrees, we could go all the way up here. We know that from our geometry days. If we were to make a straight angle, then we know that this is going to be 180 degrees. And then if we were to go another 90 degrees, that'd be 270 degrees. And part of this we already did from example 1. So this is 45 degrees, this is 135 degrees over here, 225 degrees, and then finally 315 degrees. All right, so if we were to break it up into even more pieces, we sort of have this angle is equal to this angle, which is equal to that angle. So we've taken our 90-degree angle and we've broken it up into 3 pieces. And so because of that, we can say that this is 30 degrees, because 90 divided by 3 is 30. And so if this is 30 degrees, 30 plus 30 is 60. And just to make sure we did it right, 60 plus 30 is 90. So, you know, we did do that right. Great. So if I were to continue adding 90 plus 30, that gives me 120. 120 plus 30 is 150. 150 plus 30 is 180. 180 plus 30 is 210. Add 30 again to get 240. Add 30 to get 270. Add 30 to get 300. 300 plus 30 is 330. And then if we go one more time, we end up with 360 as our final spot. So, which makes sense because a circle is 360 degrees all the way around. So now what I can do is I can actually take my degrees and I can follow the formula. All right, remember that formula. So that's the wrong color. The formula is you take your degrees and you multiply it by pi over 180. So if I were to multiply this, I'm going to end up with 0, really, or 0 pi. I want to keep the pi so that I know, you know, I turned it into radians. If I take the next piece, 30 degrees times pi over 180. All right, that's going to give me 30 pi over 180, which is the same thing as pi over 6. You could write it as like 1/6 pi, but I like this one more, and typically this is how it's going to be written just because it's, I don't know, it's smaller, I guess, but it's just typically how people write this. So we can say that this is pi over 6. Same thing again, 45 times pi over 180. That's going to give me pi over 4. So I'm going to write that over here, pi over 4. Then the next one is going to end up, it's going to give me pi over 3. And then 90 times pi over 180. This is going to give me 1/2 pi, or pi over 2. All right, so I just went ahead and did all of this. You can do the rest on your own, or you can look at my answer key to see which one, or, you know, if you did correctly, or to copy it down. But these are the most common degrees and their corresponding radian measures. And this is really useful for whenever we get to our problems in a couple of seconds. All right, so let's do our last example, which is now we are going to apply our radians, which is our measurements. We're going to apply those radians in real-world examples. So some things we have to know from geometry is that we have our arc length. Arc length is, again, our distance. Okay, so typically our distance is going to be written in just our units, whatever units we get. That's the end of our answer. Okay, just make sure you include that. But for our area, remember, for those of you who were in geometry and in my class, with the area, that's of course our inside area right here. And so for this one, our answer is going to be written as units squared. So whatever they give us, centimeters squared, feet squared, meters squared, whatever it is, just make sure it has squared so we know we're talking about the area. All right, so example 4.1 says, given the measurements for a softball field, find the length of the outfield fence. Okay, so that length of the outfield fence, that is our, that is going to be our arc length of the outfield fence. So that's this outside area here. And then after that, they ask us to find our area of the field, and that is going to be all the area in here. All right, so that part is done. Make sure to fill it all in so we're all good. All right, so let's go ahead and get started by using our formulas. First things first, let's do that arc length. S is going to equal R times theta. Our radius is 200 feet, so we'll fill that in. And the next part is theta. Our theta is at a 90-degree angle, but remember, our 90-degree angle is the measurement of that corner. It's not really the measurement of how far it is. So we need to change that 90 degrees into radians. So we're going to multiply it by pi over 180. And if you have finished that circle that we did earlier, you should automatically just be able to look at the 90 degrees and see that we sort of already have the answer already, which is going to be pi over 2. So for theta, instead of plugging in my degrees, I'm going to plug in my radians, and I'm going to end up with 100 pi, which is approximately 314 feet. So this is my answer, or first answer, I should say. So now I'm going to keep going, and I'm going to do our area. Area is going to equal 1/2 r squared times theta. Plug in our pieces, 1/2 200 squared times, again, pi over 2. This is going to give me 10,000 pi, which is approximately 31416. And since we're talking about feet, we're going to square it. So really this is 31,416 feet. All right, so that one's pretty easy, very straightforward. Example 4.2 is a little bit different. It says, and it's a little hard to see on your notes, so I do apologize for that, but it should be 14 inches here, and this should be 25 inches. All right, so it says the rear window shield wiper of a car rotates 120 degrees as shown. Find the area cleared by the wiper. So notice how it's not the full 25 inches, it's actually 14 inches. And so an easy way to do this is just apply the area formula to our 14 and to our 25 inches to find the total, and then we can subtract any extra, okay? So we're gonna, if we wanted to sort of write this out, we know that the area is gonna equal sort of our longer side subtracted by our shorter side. And so you have to understand something really fast. You have to understand that from here to here is 25 inches, right? We do want the 14, but what we don't want is this sort of empty space right here. So think about it as like 25 minus 14, okay? So the total length minus the piece that we do want gives us 11. So this empty space is 11. So I'm gonna write shorter side here, but really it's because of the 11 right here, the empty space that's not being cleaned. All right, so I'm going to do my two formulas. Area equals our total, our long side. So that's 1/2 times 25 squared. All right, we're going to change 120 into radians, so times pi over 180, which is going to give me 2 pi over 3. So 2 pi over 3. If I type this into my calculator without pi, remember, and change it into a fraction, it's going to be 625 pi over 3. So this is my long side, so if I want 625 pi over 3. And now I'm going to do the same thing again with my shorter side, or my empty space, okay? This leaves my 14 inches there, okay? So I'm going to say 1/2 times 11 squared times 2 pi over 3. And if I do that, I'm going to end up with 121 pi over 3. So I'm going to take this 121 pi over 3, and I'm going to subtract it in my calculator. Again, I strongly recommend that you leave off pi and just tack it on at the end. So I'm just typing it in my calculator, 625 divided by 3 minus 121 divided by 3, and I'm using parentheses around each of my fractions, okay? So it's like parentheses 625 divided by 3, parentheses, minus, and then parentheses again. So if you do that correctly, you should end up with 168, tack on pi at the end, and it is times pi. And I am going to go ahead and just find what is, you know, that approximately. So I'm going to multiply it by pi, not 3.14, but pi. And it is approximately 520, I'll round to the nearest inch, 528 inches squared. And so this is our answer. It's a little cramped, sorry. I think you guys end up with more room than I do on here, so my bad. But it should be about 528 inches squared. All right, hope that was helpful. Please make sure you're checking PLUS portals and Teams for your homework assignments. And if you have any questions, please reach out.